The limits of early atomic theory became apparent only after centuries of scientific progress had given researchers confidence that nature could be explained through clear, mechanical laws. For a long time, matter was believed to be continuous, and the idea that it was composed of tiny, indivisible units was more philosophical than scientific. Ancient thinkers such as Democritus proposed the concept of atoms, but without experimental evidence, these ideas remained speculative. It was not until the 19th century that atomic theory began to take a firm scientific shape, particularly through the work of John Dalton, who described atoms as solid, indivisible spheres that combined in fixed ratios to form compounds. While Dalton's theory successfully explained many chemical observations, it treated atoms as simple, featureless objects and offered no insight into their internal structure. As experimental techniques improved, scientists began to uncover phenomena that Dalton's model could not explain. The discovery of electricity and the behavior of charged particles raised new questions about the nature of matter. Experiments with cathode rays in the late 19th century revealed the existence of electrons, showing that atoms were not indivisible after all. J. Thomson's discovery of the electron forced scientists to reconsider the structure of the atom. Thomson proposed the plum pudding model, in which negatively charged electrons were embedded within a positively charged sphere. This model represented a major step forward, as it acknowledged internal components within the atom, yet it still relied heavily on classical ideas and lacked the precision needed to explain many experimental results. The limitations of early atomic theory became even clearer with the development of spectroscopy, the study of how atoms emit and absorb light. When elements were heated or electrified, they produced distinct patterns of spectral lines, acting almost like fingerprints for each element. Classical physics predicted that atoms should emit a continuous range of energies, yet experiments consistently showed discrete lines at specific wavelengths. This contradiction posed a serious challenge. Early atomic models could describe where electrons might be located, but they could not explain why electrons released energy only in specific amounts. In response to this problem, Niels Bohr introduced a revolutionary model of the atom in 1913. Bohr proposed that electrons move in fixed orbits around the nucleus and can only occupy certain allowed energy levels. When an electron jumps from one orbit to another, it emits or absorbs energy in discrete packets or quanta. This idea successfully explained the spectral lines of hydrogen and marked a turning point in atomic theory. However, Bohr's model was still a hybrid of classical and quantum ideas. It worked well for simple atoms, but failed when applied to more complex systems. Moreover, it did not fully explain why only certain orbits were allowed or what fundamentally governed electron behavior. As physicists probed deeper, they encountered further inconsistencies. One major issue was the behavior of electrons in magnetic fields. Experiments showed that spectral lines split into multiple closely spaced lines when atoms were placed in a magnetic field, a phenomenon known as the Zeeman effect. While some of this splitting could be explained by the motion of electrons in their orbits, other aspects could not. Even when orbital motion was carefully accounted for, the observed patterns did not match theoretical predictions. This mismatch highlighted a gap in the understanding of atomic structure and suggested that electrons possessed properties not yet included in existing theories. Another limitation of early atomic theory was its reliance on classical mechanics to describe microscopic behavior. Classical physics assumes that objects have definite positions and velocities, and that their motion can be predicted precisely if initial conditions are known. However, experiments at the atomic scale consistently contradicted these assumptions. The wave-like behavior of particles, demonstrated by phenomena such as electron diffraction, showed that electrons could not be treated simply as tiny billiard balls. Instead, they exhibited dual characteristics, behaving sometimes like particles and sometimes like waves. Early atomic models struggled to incorporate this duality in a consistent way. The inability of classical and early quantum models to explain fine details in atomic spectra further emphasized their limitations. Spectral lines were found to have subtle structures, known as fine structure, that could not be explained solely by electron orbits and energy levels. These fine splittings hinted at additional degrees of freedom within the atom. Scientists realized that something fundamental was missing from their description of electrons, but it was not immediately clear what that something was. At the same time, the stability of atoms posed another conceptual problem. According to classical electrodynamics, an accelerating charged particle should continuously emit radiation and lose energy. If electrons truly orbited the nucleus like planets, they should rapidly lose energy and spiral inward, causing atoms to collapse. The fact that matter is stable directly contradicted this prediction. Early atomic theories avoided this problem by imposing special rules, such as Bohr's fixed orbits, but these rules lacked deeper justification. They worked mathematically but did not arise naturally from known physical principles. These growing inconsistencies led physicists to question the adequacy of existing theories. The realization that early atomic models could not fully describe observed phenomena created a sense of crisis in physics at the beginning of the 20th century. Rather than being a sign of failure, this crisis became a driving force for innovation. Scientists began to accept that the microscopic world might follow rules fundamentally different from those governing everyday objects. The development of quantum mechanics in the mid-1920s represented a response to these limitations. New mathematical frameworks, such as wave mechanics and matrix mechanics, provided more accurate tools for describing atomic behavior. Yet even with these advances, certain experimental results still resisted explanation. The splitting of spectral lines, the behavior of atoms in magnetic fields, and the detailed structure of electron energy levels all pointed toward an additional property of electrons that had not yet been recognized. In this context, the limits of early atomic theory were not merely technical shortcomings, but conceptual boundaries. They showed that focusing only on electron charge, mass, and orbital motion was insufficient. The atom was more complex than any simple mechanical model could capture. These limitations prepared the ground for one of the most profound discoveries in modern physics, the realization that electrons possess an intrinsic quantum property independent of their motion through space. Thus, the failure of early atomic theories to explain experimental observations was essential to scientific progress. Each inconsistency served as a clue, guiding researchers toward deeper truths about the nature of matter. The recognition of these limits did not end the search for understanding. Instead, it opened the door to new ideas that would redefine physics. By exposing what early models could not explain, scientists were compelled to move beyond classical intuition and toward a richer, more accurate description of the atomic world. As research continued into the weaknesses of early atomic theory, scientists increasingly realized that the problem was not a lack of effort or precision, but a deeper issue with the assumptions underlying their models. Early theories tried to force atomic behavior into familiar classical frameworks, assuming that microscopic particles must obey the same rules as visible objects. This approach initially seemed reasonable, but experimental evidence repeatedly challenged it. The atomic world appeared to operate according to principles that had no direct counterpart in everyday experience. One of the most striking limitations was the inability of early atomic models to explain why atoms exhibited such strict regularity. Elements behaved in predictable ways, forming stable compounds and displaying consistent chemical properties. This regularity suggested an underlying order, yet classical models could not account for how electrons arranged themselves so precisely around the nucleus. If electrons were free to move according to classical laws, atoms should exhibit a wide range of unstable and chaotic configurations. Instead, matter was remarkably stable, pointing to hidden rules governing atomic structure. The periodic table itself highlighted these shortcomings. As elements were arranged according to their chemical properties, clear patterns emerged, repeating at regular intervals. Early atomic theory struggled to connect these patterns to the structure of atoms. While the number of electrons was known to influence chemical behavior, there was no clear explanation for why electrons filled atomic regions in a specific sequence, or why certain elements shared similar properties. The observed order of the periodic table hinted at a deeper organization within atoms that classical ideas could not fully describe. Another important challenge arose from precision measurements. As instruments became more sensitive, physicists detected increasingly subtle effects in atomic behavior. Small discrepancies between theoretical predictions and experimental results could no longer be dismissed as measurement errors. Instead, they pointed toward missing elements in atomic theory. These discrepancies accumulated, forming a growing body of evidence that the existing models were incomplete. Theories that worked well at a basic level failed when tested against high-precision data. The interaction between atoms and external forces further exposed the limits of early understanding. When atoms were subjected to electric or magnetic fields, their responses were more complex than predicted. The splitting of energy levels and spectral lines suggested that electrons responded not only through their orbital motion, but also through some internal mechanism. Classical physics had no clear way to describe such behavior, reinforcing the idea that electrons possessed hidden properties beyond those already known. Additionally, early atomic theory faced difficulties in explaining angular momentum at the atomic scale. In classical mechanics, angular momentum arises from an object's motion through space. However, experimental observations indicated that electrons exhibited angular momentum values that did not correspond neatly to any classical orbit. These values appeared quantized, taking on specific fixed amounts rather than a continuous range. This contradicted classical expectations and suggested that angular momentum itself might have a fundamentally different origin in the quantum world. The limitations of early atomic theory also became evident in attempts to unify atomic physics with electromagnetism. Maxwell's equations successfully described the behavior of electric and magnetic fields, but when applied to atomic systems, they led to contradictions. According to classical electrodynamics, electrons in motion should radiate energy continuously. This prediction conflicted with the observed stability of atoms and the discrete nature of atomic spectra. The failure to reconcile these theories underscored the need for a new conceptual foundation. As debates intensified within the scientific community, it became clear that progress required abandoning some long-held assumptions. Physicists began to accept that properties such as energy, momentum, and angular momentum might be inherently quantized. This shift in thinking marked a departure from deterministic classical laws toward a probabilistic description of nature. Early atomic theory had paved the way for this transition by revealing where classical ideas broke down. The recognition of these limits was not immediate or universally accepted. Many scientists were reluctant to discard models that had achieved partial success. However, the growing weight of experimental evidence made resistance increasingly difficult. Each unexplained phenomenon served as a reminder that the atom was not a miniature version of the macroscopic world, but a realm governed by its own rules. Ultimately, the shortcomings of early atomic theory played a crucial role in shaping modern physics. By clearly defining what could not be explained, they guided researchers toward new questions and new approaches. These limitations encouraged the development of quantum mechanics and prepared scientists to accept revolutionary ideas, including the existence of intrinsic particle properties. The realization that electrons might possess internal characteristics unrelated to their motion emerged directly from attempts to resolve the failures of earlier models. In this way, the limits of early atomic theory were not obstacles but stepping stones. They revealed the boundaries of classical reasoning and highlighted the need for a deeper, more abstract understanding of matter. By confronting these limits, physicists opened the door to discoveries that transformed science, leading to a more complete and accurate picture of the atomic world and setting the stage for the identification of entirely new quantum properties. The discovery of unexpected electron behavior marked a decisive moment in the history of physics, as it revealed that electrons did not behave in the simple, predictable ways scientists had long assumed. When the electron was first identified at the end of the 19th century, it was understood primarily as a tiny particle carrying negative electric charge. This discovery alone was revolutionary, but early interpretations still framed the electron within classical physics. Scientists believed that once the electron's charge and mass were known, its behavior could be fully explained using established mechanical and electromagnetic laws. However, as experimental methods improved, electrons began to exhibit behaviors that contradicted these expectations and forced physicists to rethink their assumptions. One of the earliest signs of unexpected electron behavior came from experiments involving electricity in gases and vacuum tubes. Cathode ray experiments showed that electrons could be deflected by electric and magnetic fields, confirming that they carried charge. Yet these same experiments revealed that electrons behaved identically regardless of the material from which they were emitted. This universality was surprising. If electrons were components of atoms, scientists expected their properties to vary depending on the substance involved. Instead, electrons appeared to be fundamental and identical in all circumstances, hinting that they were not merely fragments of atoms, but basic building blocks of matter. Further surprises emerged when scientists studied how electrons moved within atoms. According to classical expectations, electrons orbiting a nucleus should be able to occupy a wide range of energies and positions. Instead, experiments showed that electrons seemed restricted to specific energy states. When electrons absorbed energy, they did not gradually increase their speed or distance from the nucleus. Rather, they jumped abruptly between distinct levels. This behavior defied classical intuition and suggested that electrons followed rules that had no counterpart in everyday mechanics. Unexpected behavior also appeared when electrons interacted with light. Classical physics treated light as a wave and electrons as particles, but experiments began to blur this distinction. In the photoelectric effect, light striking a metal surface caused electrons to be ejected, but only if the light had a minimum frequency. Increasing the intensity of low-frequency light did nothing, while even faint high-frequency light could eject electrons instantly. This contradicted wave-based predictions and showed that electrons responded to light in a quantized manner. The electron's response depended not on the total energy delivered, but on the energy of individual light quanta, revealing a new and surprising relationship between matter and radiation. As researchers continued to investigate electron behavior, magnetic effects produced further anomalies. When beams of electrons passed through magnetic fields, their paths bent in precise ways that allowed scientists to measure their properties. However, in atomic systems, magnetic fields caused atoms to behave in unexpectedly complex patterns. Spectral lines split into multiple components, indicating that electrons were sensitive to magnetic influences beyond what orbital motion alone could explain. These effects suggested that electrons possessed additional characteristics that determined how they interacted with magnetic fields. Electron scattering experiments added another layer of mystery. When electrons were fired at thin metal foils, they did not always behave like classical particles following predictable trajectories. Instead, they produced interference patterns similar to those created by waves. This wave-like behavior of electrons was profoundly unexpected. It suggested that electrons could not be fully described as particles with well-defined paths. Instead, they exhibited a dual nature, acting as both particles and waves depending on how they were observed. This duality challenged the foundations of physics. If electrons could behave like waves, then concepts such as position and momentum could no longer be defined with absolute certainty. Experiments showed that attempts to measure an electron's position precisely disrupted its momentum, and vice versa. This was not due to experimental imperfections, but was an inherent feature of electron behavior. The realization that electrons obeyed probabilistic rather than deterministic laws marked a dramatic departure from classical thinking. Unexpected electron behavior also emerged in the context of chemical bonding. Early models assumed that electrons simply orbited nuclei independently, but chemical experiments showed that electrons could be shared between atoms, forming bonds that held molecules together. The way electrons arranged themselves in molecules could not be explained by simple orbits. Instead, electrons appeared to occupy regions of space influenced by multiple nuclei at once, behaving in ways that reflected their wave, like nature. This behavior was essential for explaining molecular shapes, bond strengths, and chemical reactions. The behavior of electrons at very low energies revealed still more surprises. In some materials, electrons flowed with little resistance, a phenomenon later understood as superconductivity. In others, electrons became locked into rigid patterns, leading to insulating behavior. These collective effects showed that electrons did not always act independently. Instead, their behavior could be strongly influenced by interactions with other electrons and with the atomic lattice. Such collective phenomena could not be explained by treating electrons as isolated classical particles. Even the simple act of confining electrons led to unexpected results. When electrons were trapped in small regions of space, such as in atoms or artificial structures, their allowed energies became quantized. The smaller the region, the greater the separation between energy levels. This quantization was not an arbitrary feature, but a direct consequence of the electron's wave, like nature. It showed that spatial confinement fundamentally altered electron behavior, further distancing it from classical expectations. These discoveries gradually convinced physicists that the electron was far more complex than originally believed. It was not merely a charged particle following predictable paths, but an entity governed by quantum rules that defied everyday logic. Each unexpected behavior served as evidence that existing theories were incomplete and that a deeper framework was required. The accumulation of these experimental results transformed the electron from a simple component of atoms into a central figure in the development of quantum theory. Its strange responses to light magnetic fields and confinement revealed that nature at small scales operates according to principles fundamentally different from those of the macroscopic world. These findings did not immediately provide clear answers, but they raised essential questions that guided further research. In retrospect, the discovery of unexpected electron behavior was not a single event, but a gradual realization built from many experiments. Each anomaly challenged physicists to abandon familiar assumptions and explore new ideas. By revealing the limits of classical descriptions, these discoveries prepared the scientific community to accept revolutionary concepts about matter and energy. This growing awareness set the stage for even more profound insights into the nature of electrons. The realization that electrons behaved in ways no classical model could fully explain opened the door to the identification of new intrinsic properties. What began as puzzling experimental results ultimately led to a deeper understanding of the quantum world, reshaping physics and laying the groundwork for discoveries that would redefine the fundamental nature of reality. As investigations continued, the unexpected behavior of electrons increasingly appeared not as isolated curiosities, but as consistent patterns pointing toward a deeper underlying reality. Physicists began to notice that no matter how carefully they refined classical models, the same anomalies reappeared. This repetition suggested that the strange behavior was not due to experimental error or incomplete measurement, but rather an intrinsic feature of electrons themselves. The more precisely electrons were studied, the more clearly they departed from classical expectations. One important area where this became evident was in high-precision measurements of atomic spectra. When scientists examined spectral lines with greater resolution, they found subtle splittings and shifts that earlier experiments had overlooked. These fine details revealed that electrons were influenced by factors beyond simple energy levels. Even when temperature, pressure, and external fields were carefully controlled, unexplained variations remained. These observations reinforced the idea that electrons possessed internal degrees of freedom that were not yet understood. Unexpected behavior also appeared in electron interactions with magnetic fields at the individual particle level. When electrons were passed through carefully arranged magnetic field gradients, they separated into distinct paths rather than forming a continuous spread. This discrete behavior was astonishing because classical physics predicted a smooth distribution of outcomes. Instead, electrons seemed to choose between specific orientations when interacting with magnetic fields. This finding challenged the notion that an electron's properties could vary continuously and suggested that some aspects of electron behavior were inherently quantized. The growing realization that electrons responded to magnetic fields in discrete ways had profound implications. It implied that electrons carried a form of angular momentum not directly linked to their motion through space. Classical theory allowed angular momentum only through rotation or orbital motion, yet experiments hinted at a built-in property that existed even when electrons were not moving in an orbit. This behavior could not be explained by any classical analogy and pointed toward a fundamentally new concept within physics. Unexpected electron behavior was also evident in solid materials. As researchers studied electrical conductivity, they found that electrons in metals behaved differently from those in insulators and semiconductors. In some cases, electrons moved freely, conducting electricity with ease. In others, they appeared localized, unable to carry current. These differences could not be fully explained by simple particle collisions or classical forces. Instead, they depended on quantum rules governing how electrons occupied energy states within materials. This behavior revealed that electrons were sensitive to the collective environment of atoms in ways that classical theory could not describe. Experiments involving extremely low temperatures further deepened the mystery. Under such conditions, electrons began to behave in coordinated ways, forming collective quantum states. Phenomena such as superconductivity and superfluidity demonstrated that electrons could move without resistance or lock into shared patterns. These effects were entirely unexpected from a classical perspective, which treated particles as independent entities. The emergence of collective electron behavior emphasized that electrons followed quantum principles that only became visible under certain conditions. Another striking aspect of unexpected electron behavior involved measurement itself. Scientists realized that observing an electron inevitably altered its behavior. Attempts to determine an electron's position disrupted its momentum, and vice versa. This was not a limitation of experimental tools, but a fundamental feature of nature. The act of measurement played an active role in shaping electron behavior, undermining the classical idea of an objective, observer-independent reality at the microscopic level. As these insights accumulated, physicists began to see electrons less as tiny objects and more as quantum entities described by probability. Instead of definite paths, electrons were associated with probability distributions that predicted where they were likely to be found. This probabilistic view explained many of the previously mysterious behaviors, such as interference patterns and quantized energy levels. However, it also introduced philosophical challenges, forcing scientists to reconsider long-held ideas about causality and determinism. The unexpected behavior of electrons also influenced the development of new mathematical tools. Traditional equations based on Newtonian mechanics proved inadequate. In their place, new formalisms were developed to capture the wave-like and probabilistic nature of electrons. These mathematical descriptions did not provide intuitive pictures but offered remarkably accurate predictions. The success of these methods confirmed that electrons truly operated according to quantum rules. Over time, the scientific community came to accept that electron behavior could not be fully visualized using classical imagery. Terms such as orbit and trajectory were replaced by more abstract concepts. This shift marked a profound change in how physicists understood the microscopic world. Electrons were no longer seen as miniature planets or billiard balls, but as quantum objects with unique and sometimes counterintuitive properties. The recognition of unexpected electron behavior ultimately reshaped the goals of atomic physics. Instead of trying to force new observations into old frameworks, scientists embraced the need for entirely new principles. Each anomaly became a clue rather than a problem, guiding researchers toward deeper insights. The electron emerged as a key to unlocking the mysteries of the quantum world. In hindsight, these discoveries represent a turning point in scientific thought. The unexpected behavior of electrons revealed the limits of classical reasoning and demonstrated that nature operates differently at small scales. By confronting these surprises, physicists were led to uncover new quantum properties that would transform technology, chemistry, and our understanding of reality itself. The concept of electron spin as an intrinsic property represents one of the most profound shifts in the understanding of matter at the quantum level. As physicists struggled to explain the growing list of experimental anomalies associated with electron behavior, it became increasingly clear that existing descriptions were incomplete. Early atomic models focused on electrons as particles moving through space, characterized by their mass, charge, and orbital motion around the nucleus. However, repeated experimental results suggested that electrons possessed a deeper, internal characteristic that could not be explained by motion alone. This realization marked the beginning of a new way of thinking about fundamental particles. The idea of an intrinsic property was itself revolutionary. In classical physics, properties such as angular momentum arise from motion. An object rotates or revolves, and this movement produces measurable effects. For macroscopic objects, angular momentum can always be traced back to some form of physical rotation. When scientists observed effects in electrons that resembled angular momentum, their first instinct was to attribute these effects to orbital motion within the atom. Yet this explanation quickly proved insufficient. Even when orbital contributions were fully accounted for, experiments continued to reveal additional angular momentum, like behavior that had no clear classical origin. This unexplained behavior became especially apparent in atomic spectroscopy. The fine structure of spectral lines showed that energy levels were split in subtle but consistent ways. These splittings could not be fully explained by known interactions or by the motion of electrons in their orbits. The regularity of the observed patterns suggested that the effect was fundamental rather than accidental. Something inherent to the electron itself appeared to be influencing how it interacted with magnetic fields and how its energy levels were arranged. To address this mystery, physicists proposed that the electron possesses an intrinsic form of angular momentum, independent of any motion through space. This property came to be known as spin. Unlike classical rotation, spin does not involve the electron physically spinning around an axis in space. Instead, it is a purely quantum mechanical property that exists as part of the electron's identity. Every electron has spin, just as every electron has mass and electric charge. It is not something an electron can gain or lose, it is an inseparable aspect of what an electron is. The intrinsic nature of spin distinguished it sharply from earlier concepts. Orbital angular momentum depends on how an electron moves and where it is located. Spin, by contrast, exists even if the electron is at rest relative to the nucleus. This was a radical departure from classical thinking, which offered no clear analogy for such a property. Attempts to visualize spin as literal rotation quickly ran into contradictions, such as the implication that parts of the electron would have to move faster than the speed of light. These inconsistencies made it clear that spin could not be understood through classical imagery. Instead, spin had to be accepted as a fundamental quantum property, defined mathematically rather than visually. It manifested itself through measurable effects, particularly in the way electrons responded to magnetic fields. Electrons behaved as if they carried tiny magnetic moments, and these moments were directly linked to spin. The fact that these magnetic effects were observed consistently across different experiments reinforced the idea that spin was intrinsic and universal. One of the most striking features of electron spin was its quantized nature. Measurements showed that spin could take on only specific values, rather than a continuous range. For electrons, spin is always found to have the same magnitude, and it can be oriented in only certain allowed ways relative to an external magnetic field. This discreteness was a hallmark of quantum behavior and stood in stark contrast to classical expectations, where angular momentum can vary smoothly. The acceptance of spin as an intrinsic property helped resolve several long-standing problems in atomic physics. It provided a natural explanation for the fine structure of atomic spectra and clarified why certain energy levels were split even in the absence of obvious external influences. By incorporating spin into atomic models, physicists were able to achieve much closer agreement between theory and experiment. What had once appeared as mysterious discrepancies now made sense within a broader quantum framework. Spin also played a crucial role in explaining the organization of electrons within atoms. When combined with other quantum principles, the concept of intrinsic spin led to a deeper understanding of why electrons fill atomic states in a specific order. The presence of spin meant that electrons were not identical in every respect. Their spin orientation distinguished them in a fundamental way. This insight was essential for explaining how multiple electrons could occupy similar energy levels without violating quantum rules. Beyond atomic structure, the concept of intrinsic spin reshaped the understanding of particle identity itself. It suggested that particles are defined not only by how they move, but by internal properties that have no classical counterpart. This idea extended beyond electrons to other particles, revealing a rich hierarchy of intrinsic characteristics that govern how particles interact and behave. Spin became a central concept in particle physics, influencing theories that describe the fundamental forces of nature. The introduction of spin also challenged philosophical assumptions about the nature of physical reality. Because spin cannot be visualized directly, it forced scientists to rely on abstract mathematical descriptions rather than intuitive pictures. This marked a broader shift in physics toward accepting that the deepest aspects of nature may not be directly accessible to human intuition. Instead, they must be understood through consistent theoretical frameworks supported by experimental evidence. As the concept of electron spin gained acceptance, it became clear that it was not an optional addition to atomic theory, but an essential component. Without it, the behavior of electrons could not be fully explained, and many experimental results would remain mysterious. Spin unified a wide range of observations under a single principle, demonstrating the power of abstract concepts in advancing scientific understanding. In this way, the recognition of electron spin as an intrinsic property represented more than a technical correction to existing models. It signaled a fundamental change in how physicists understood matter at its most basic level. Electrons were no longer seen merely as point charges in motion, but as quantum entities with internal characteristics that shape their interactions and define their behavior. This realization laid the foundation for deeper insights into the quantum world and prepared the way for further discoveries that continue to influence modern science. As the idea of electron spin matured, physicists began to explore its implications more deeply, and in doing so they uncovered a richer and more subtle picture of the electron than ever before. What initially appeared as a theoretical adjustment soon revealed itself as a cornerstone of quantum physics. The intrinsic nature of spin meant that it could not be derived from any underlying motion or structure within the electron, it simply existed as a fundamental attribute. This realization forced scientists to rethink how properties were assigned to particles and how those properties manifested in experiments. One of the most revealing aspects of electron spin was how it influenced measurement outcomes. When electrons were subjected to magnetic fields, their spin caused them to behave as if they were tiny bar magnets. However, these magnetic moments did not vary continuously, as classical intuition would suggest. Instead, they aligned only in specific, allowed orientations. This behavior demonstrated that spin imposed strict constraints on how electrons could interact with their environment. The outcome of a measurement was not predetermined in a classical sense, but emerged from the quantum rules governing spin. The discovery that spin had only certain allowed orientations introduced a new form of quantization into physics. Unlike orbital motion, which depends on external conditions such as energy and position, spin quantization appeared to be an internal rule. Every electron, regardless of where it was or how it was produced, exhibited the same spin behavior. This universality strengthened the argument that spin was not a secondary effect, but a defining characteristic of the electron itself. Spin also played a crucial role in shaping the collective behavior of electrons in atoms and materials. When multiple electrons occupied the same atomic region, their spins influenced how they arranged themselves. Electrons could not all occupy identical states. Their intrinsic spin distinguished them from one another. This property explained why atoms have structured electron configurations and why chemical elements exhibit distinct and repeating properties. Without the inclusion of spin, the observed structure of matter would remain unexplained. As theoretical understanding advanced, spin became deeply embedded in the mathematical framework of quantum mechanics. New equations were developed to incorporate spin naturally into the description of particles. These equations did not treat spin as an add-on but as an essential component of the particle's quantum state. The success of these theories in predicting experimental results further confirmed that spin was a real and necessary aspect of physical reality. The intrinsic nature of spin also had profound implications beyond atomic physics. It influenced how electrons interact with one another and with electromagnetic fields. Spin-dependent interactions were found to underlie many physical phenomena, including magnetism in solids. The alignment of electron spins within materials explained why some substances exhibit magnetic properties while others do not. This connection between a microscopic quantum property and macroscopic behavior highlighted the far-reaching impact of spin. Another important consequence of recognizing spin as intrinsic was the shift it caused in scientific intuition. Physicists had to accept that not all properties could be visualized or reduced to mechanical motion. Spin existed as an abstract quantity, defined by mathematical rules and revealed through experiments. This acceptance marked a broader transformation in physics, where abstract concepts became central to understanding nature at its deepest level. Spin also influenced the emerging understanding of symmetry and conservation laws in physics. The behavior of spin under transformations, such as rotations, revealed deep connections between particle properties and the fundamental structure of space. These insights contributed to the development of more advanced theories that sought to unify different aspects of physical law. In this sense, the intrinsic nature of spin served as a bridge between atomic physics and more general principles governing the universe. Over time, the concept of electron spin proved essential for interpreting new experimental discoveries. As technology advanced and experiments became more precise, spin-related effects continued to appear. Rather than being anomalies, these effects fit naturally within the framework that treated spin as intrinsic. This consistency reinforced confidence in the concept and encouraged its application to other particles beyond the electron. The recognition of spin as an intrinsic property also reshaped the way scientists classified particles. Spin became one of the fundamental criteria used to distinguish different types of particles and to predict their behavior. This classification system revealed patterns and regularities that would have been invisible without the concept of spin. It demonstrated that intrinsic properties play a central role in organizing the physical world. In the broader context of scientific discovery, the acceptance of electron spin illustrated how progress often requires abandoning familiar ways of thinking. Classical ideas had to be set aside to make room for a concept that could not be directly visualized or intuitively understood. Yet by embracing this abstraction, physicists gained a more accurate and comprehensive understanding of reality. Ultimately, The exploration of electron spin as an intrinsic property transformed the study of matter. It provided answers to long-standing questions while raising new ones, driving further research and innovation. Spin emerged not as a minor detail, but as a fundamental feature that shapes the behavior of electrons and the structure of the universe itself. Through this realization, physics advanced into a new era, one in which the deepest truths of nature are revealed not through simple pictures, but through carefully tested and mathematically precise ideas. The acceptance of electron spin as a real physical property was not based on theory alone. It was firmly grounded in experimental evidence that consistently pointed toward the existence of an intrinsic quantum characteristic. As physicists explored atomic behavior with increasing precision, experiments began to reveal effects that could not be explained unless electrons possessed an internal form of angular momentum. These experiments provided concrete proof that spin was not a mathematical invention, but a measurable and essential feature of electrons. One of the earliest and most convincing pieces of evidence came from experiments involving magnetic fields and atomic spectra. When atoms were placed in an external magnetic field, their spectral lines were observed to split into multiple components. While some of this splitting could be explained by the orbital motion of electrons, a significant portion remained unexplained. Even when theoretical calculations accounted for all known orbital effects, the observed patterns did not fully match predictions. This discrepancy strongly suggested the presence of an additional magnetic influence originating from the electrons themselves. A landmark experimental confirmation emerged from beam experiments in which particles were passed through non-uniform magnetic fields. When electrons traveled through such fields, they did not spread out in a continuous range of directions as classical physics predicted. Instead, they separated into discrete paths. This behavior demonstrated that electrons interacted with magnetic fields in quantized ways, consistent with the idea that they carried an intrinsic magnetic moment. The only plausible explanation for this discrete deflection was that electrons possessed an internal property with fixed orientations, later understood as spin. Further experimental support came from precise measurements of magnetic moments. Scientists found that electrons behaved like tiny magnets, with a magnetic strength that could be measured accurately. Importantly, this magnetic moment did not arise solely from the electron's orbital motion around the nucleus. Even free electrons not bound within atoms exhibited magnetic behavior. This observation was crucial because it ruled out explanations based entirely on orbital effects and reinforced the conclusion that the magnetic moment was intrinsic to the electron itself. The interaction between electrons and electromagnetic radiation also provided strong evidence for spin. When electrons absorbed or emitted energy, subtle shifts in energy levels were observed that depended on their magnetic properties. These shifts were consistently reproduced across different experiments and materials. The predictable nature of these effects indicated an underlying universal property of electrons, rather than an accidental feature of specific atomic systems. Another important line of evidence came from scattering experiments. When electrons were scattered off atoms or other particles, the outcomes depended on the relative orientations of their intrinsic properties. Certain scattering patterns could only be explained if electrons had an internal angular momentum that influenced how they interacted. These results matched theoretical predictions that included spin, providing further confirmation of its physical reality. The behavior of electrons in solids offered additional experimental support. Magnetic properties of materials, such as ferromagnetism, were found to arise from the alignment of electron spins within atoms. Experiments showed that when many electron spins aligned in the same direction, strong magnetic effects emerged at the macroscopic level. This connection between microscopic spin and large-scale magnetism demonstrated that spin was not merely an abstract concept, but a property with observable consequences in everyday materials. Spectroscopic techniques continued to refine the evidence for spin. As instruments improved, scientists could detect increasingly fine details in atomic spectra. These fine structures matched theoretical models that incorporated electron spin with remarkable accuracy. Without spin, the theoretical predictions failed to match experimental data. The consistent agreement between experiment and theory strengthened confidence in spin as a fundamental property. Perhaps most compelling was the reproducibility of spin-related effects. No matter how or where electrons were studied, whether in atoms, beams, or solid materials, the same spin characteristics appeared. This universality left little doubt that spin was an intrinsic feature of electrons, independent of external conditions. It confirmed that spin was as fundamental as mass or charge. Together, these experiments transformed electron spin from a speculative idea into an established physical reality. Each piece of evidence reinforced the others, building a coherent picture supported by observation and measurement. Through careful experimentation, physicists demonstrated that electrons possess an intrinsic quantum property that profoundly influences their behavior. This experimental foundation not only validated the concept of spin, but also paved the way for its central role in modern physics and technology. Understanding the difference between classical rotation and quantum spin is essential for grasping why electron spin represents a fundamentally new idea in physics rather than a refined version of an old one. At first glance, the word spin suggests a familiar image: a solid object rotating around an axis, much like a spinning top or a rotating planet. In classical physics, rotation is a clear and intuitive concept. An object spins because different parts of it move in circles around a central axis, and its angular momentum can be calculated directly from its mass, shape, and speed of rotation. This type of rotation always has a physical cause and a visible motion through space. When scientists first encountered evidence of angular momentum, like behavior in electrons, it was natural to attempt a classical explanation. They imagined the electron as a tiny charged sphere spinning on its axis, producing a magnetic effect similar to a current loop. However, this analogy quickly failed when examined closely. Calculations showed that if an electron were physically rotating in this way, parts of it would have to move faster than the speed of light in order to produce the observed magnetic effects. Since nothing can exceed the speed of light, this interpretation was clearly impossible. This realization forced physicists to abandon the idea that electron spin could be explained as literal rotation. Quantum spin differs from classical rotation in its origin and nature. Classical rotation arises from motion through space, while quantum spin exists even when there is no spatial motion at all. An electron can be completely free or at rest relative to an observer and still possess spin. This shows that spin is not caused by movement in space, but is instead an intrinsic property of the particle. It is part of the electron's identity, much like its mass or electric charge, and does not depend on external conditions or forces. Another crucial difference lies in how these two forms of angular momentum behave. In classical physics, angular momentum can take on any value, changing smoothly as an object spins faster or slower. Quantum spin, by contrast, is quantized. Electrons always have the same amount of spin, and only certain orientations of that spin are allowed. When measured, an electron's spin does not yield a continuous range of values, but instead produces specific, discrete outcomes. This behavior has no classical counterpart and highlights the fundamentally quantum nature of spin. The way classical rotation and quantum spin interact with measurement also differs dramatically. In classical mechanics, measuring an object's rotation does not alter its basic properties. In the quantum world, however, measuring spin plays an active role in determining the outcome. When an electron's spin is measured along a particular direction, the result is not revealed as a pre-existing value in the classical sense. Instead, the act of measurement forces the spin into one of the allowed orientations. This dependence on measurement reflects the probabilistic nature of quantum mechanics and has no analogy in classical rotation. Magnetic behavior further illustrates the distinction between classical rotation and quantum spin. A rotating charged object produces a magnetic field due to the movement of charge. While electron spin is associated with a magnetic moment, this magnetism does not arise from charge moving through space. Instead, it emerges from the intrinsic quantum property of spin itself. The strength and behavior of this magnetic moment can be predicted accurately using quantum theory, even though there is no physical rotation taking place. Classical rotation also depends on the size and shape of an object. Larger objects with more mass generally have greater angular momentum for a given rotational speed. Quantum spin, on the other hand, does not depend on size or structure. Electrons are treated as point-like particles with no internal dimensions, yet they possess spin. This further emphasizes that spin cannot be understood in terms of classical geometry or mechanical motion. The difference between classical rotation and quantum spin also has important consequences for how particles interact. In systems with many electrons, classical rotation would suggest a wide range of possible behaviors. Quantum spin imposes strict rules instead. The intrinsic spin of electrons determines how they can occupy energy states and how they interact with one another. These rules shape the structure of atoms, the behavior of materials, and the properties of matter itself. Ultimately, the distinction between classical rotation and quantum spin marks a clear boundary between classical and quantum physics. Classical rotation is intuitive, visual, and continuous, while quantum spin is abstract, discrete, and fundamentally probabilistic. Recognizing this difference was essential for accepting spin as a new quantum property rather than a classical phenomenon in disguise. By understanding that electron spin is not a tiny object spinning in space, but an intrinsic feature governed by quantum laws, physicists gain deeper insight into the nature of matter and the limitations of classical ideas. The impact of electron spin on atomic structure is one of the most important consequences of its discovery, because it explains why atoms are organized, stable, and diverse in their behavior. Before the concept of spin was introduced, atomic models struggled to account for the way electrons arranged themselves around the nucleus. Energy levels alone could not fully explain the observed structure of atoms or the repeating patterns seen in the periodic table. The inclusion of electron spin provided the missing piece that brought order and consistency to atomic theory. One of the most significant effects of electron spin is its role in determining how electrons occupy atomic energy states. Electrons are governed by strict quantum rules that limit how they can be arranged within an atom. Spin gives electrons an additional identifying property, allowing multiple electrons to exist within the same energy level without violating quantum restrictions. Each electron's spin orientation distinguishes it from others, making complex atomic structures possible. Electron spin is central to the principle that no two electrons in an atom can be completely identical in all quantum properties. This rule ensures that electrons fill available energy states in a specific sequence, rather than all collapsing into the lowest possible state. As a result, electrons occupy shells and subshells at increasing energies, forming the layered structure of atoms. This arrangement explains why atoms have finite sizes and why matter is stable. The influence of spin also extends to the detailed structure of atomic energy levels. Interactions between an electron's spin and its motion around the nucleus cause small shifts and splittings in energy levels. These fine details affect how atoms absorb and emit light, producing the characteristic spectral lines used to identify elements. Without considering spin, these spectral patterns would remain unexplained or inaccurately described. Spin also plays a key role in determining the chemical behavior of atoms. The way electrons are arranged in the outermost regions of an atom largely determines how that atom interacts with others. Because spin influences how electrons fill these outer states, it indirectly governs chemical bonding and reactivity. Atoms with similar spin-dependent electron configurations exhibit similar chemical properties, which explains the repeating patterns observed across the periodic table. The stability of atoms is another area where electron spin has a profound impact. If electrons were not subject to spin-related rules, they could all occupy the same low-energy state, leading to a collapse of atomic structure. Spin prevents this by enforcing limits on electron occupancy, ensuring that electrons spread out into higher energy states. This distribution balances the attractive force of the nucleus and prevents atoms from shrinking indefinitely. Electron spin also affects how atoms respond to external magnetic fields. The combined spins of electrons within an atom determine its overall magnetic behavior. Some atoms exhibit magnetic properties because the spins of their electrons align in particular ways, while others do not. This behavior is deeply connected to atomic structure and would be impossible to understand without considering spin. In more complex atoms, the interaction between the spins of multiple electrons leads to a rich variety of atomic states. These interactions influence the atom's total angular momentum and energy, affecting how it behaves in different environments. Such effects are essential for understanding atomic transitions, selection rules, and the stability of excited states. Ultimately, electron spin provides a unifying framework for understanding atomic structure. It explains why electrons arrange themselves in orderly patterns, why atoms have distinct identities, and why matter remains stable under a wide range of conditions. By incorporating spin into atomic models, physicists were able to move beyond simple approximations and develop a more complete and accurate picture of the atom. The impact of electron spin reaches from the smallest details of atomic spectra to the large-scale organization of the elements, making it a cornerstone of modern atomic theory. The importance of electron spin in modern technology cannot be overstated, as this once purely theoretical concept now lies at the heart of many technologies that shape everyday life. What began as an attempt to explain puzzling atomic behavior has evolved into a practical tool that enables advanced medical devices, digital information systems, and emerging quantum technologies. Electron spin has moved from abstract quantum theory into real-world applications, demonstrating the powerful connection between fundamental science and technological progress. One of the most significant technological applications of electron spin is in medical imaging, particularly magnetic resonance imaging. This technology relies on the interaction between magnetic fields and the intrinsic spin of particles within the human body. When placed in a strong magnetic field, these spins align in specific ways and respond to carefully controlled radio signals. The signals emitted as the spins return to their original states are detected and used to construct highly detailed images of internal organs and tissues. The precision and safety of this imaging method depend directly on the predictable behavior of spin at the quantum level. Electron spin is also essential to modern data storage and information technology. Traditional electronic devices rely mainly on the charge of electrons to process information. However, the spin of electrons adds a new dimension. In magnetic storage devices, information is encoded in the orientation of electron spins within tiny magnetic regions. The ability to control and detect these spin orientations allows massive amounts of data to be stored in compact and reliable formats. Advances in this area have driven the development of smaller, faster, and more energy-efficient storage technologies. The field of spin-based electronics has emerged as a direct result of understanding electron spin. In these technologies, both the charge and spin of electrons are used to transmit and manipulate information. This approach offers advantages such as reduced energy consumption and increased processing speed. Devices based on spin principles are already used in sensors and memory components, and ongoing research continues to expand their capabilities. These developments illustrate how a quantum property can be harnessed for practical engineering solutions. Electron spin also plays a vital role in precision measurement and sensing technologies. Spin-sensitive devices are used to detect extremely small magnetic fields, making them valuable in scientific research, navigation, and materials analysis. The sensitivity of these devices arises from the quantized nature of spin, which responds predictably to even tiny changes in magnetic environments. Such precision would be impossible without the fundamental understanding of spin behavior. In the rapidly advancing field of quantum computing, electron spin has gained renewed importance. Quantum computers aim to use quantum properties to perform calculations far beyond the reach of classical machines. Electron spin provides a natural candidate for representing quantum information, as it can exist in multiple states and be manipulated with high precision. Research into spin-based quantum systems seeks to exploit these properties to create stable and scalable quantum processors. Electron spin is also crucial in modern communication and imaging technologies. Techniques that rely on spin interactions are used to study the structure of materials at the atomic scale, enabling the development of new materials with tailored properties. These materials, in turn, contribute to advances in electronics, energy storage, and manufacturing. The ability to understand and control spin interactions has become a powerful tool in material science. The impact of electron spin extends even into everyday consumer technologies. Devices such as smartphones, computers, and navigation systems depend indirectly on spin-based components and magnetic sensing technologies. While users may never be aware of it, the reliable performance of these devices is rooted in quantum principles discovered decades ago. Ultimately, the importance of electron spin in modern technology highlights the long-term value of fundamental scientific research. Discoveries made to solve theoretical problems have led to innovations that improve health, communication, and computing. Electron spin serves as a striking example of how abstract quantum ideas can be transformed into practical tools that shape the modern world.